this video, we are going to discuss conservation of angular momentum using an example. But before I go straight into conservation of angular momentum, let's look at a question from chapter 3, which is on conservation of linear momentum. So it says here that you have an object P, and this object P has mass of 4 kg, and it's moving with a velocity of 4 meters per second. So if I visualize the situation, I'll visualize an object P, and this object P is 4 kg, and it's moving with 4 meters per second. And then it will collide with another object, which we call it as object Q, and this object Q has a mass of 2 kg, and it moves with a velocity of 3 meters per second towards it. Then this it over here is object P lah. So object Q has 2 kg and it has a velocity of 3 meters per second moving towards P. Now they say if the two objects stick together after the collision, so it means by after the collision, they will move together, they will not separate from each other. So when you see the word stick together, you know that these two objects here will share the same common final velocity. After the collision, they should share the same velocity because they are moving together. Okay, so how we did this question is we say that the sum of linear momentum before and after are the same. Sum of linear momentum initial equals to sum of linear momentum final. Then we know that sum here, we need to look at how many objects there are in our system right now. In our system right now, there's two objects, P and Q. Therefore, our sum here will be the initial linear momentum for P and the initial linear momentum for Q and the final linear momentum for P and the final linear momentum for Q. Why do I put an X over here? Because this whole motion here is happening in the X dimension. So over here, this is actually the X component of linear momentum, the X component of linear momentum. So initial and final, yeah. So everything here, it's the X component. So if we talk about X component, then only we can introduce the sign to the velocity, which you'll see later. Okay, so you know that momentum here is just mass times velocity. So this will be mass times initial velocity, mass times initial velocity, mass times final velocity, mass times final velocity. But look over here, our initial and our final here are the X component of initial velocity, X component of initial velocity, X component of final velocity, and X component of final velocity. And because we are looking for component, right, then therefore we can put in positive and negative sign. If the component is pointing in the positive direction, then it will be a positive value for U. If the velocity is pointing in the negative direction, then you have a negative value for our X component of U. So by using subscript X, we are saying that this is a component, and if the component is positive, it's in the positive direction. If it's negative, it's pointing in the negative direction. So now, where should you assume to be positive direction? Well, usually in our sign convention, we usually take pointing to the right to be positive direction, pointing to the left to be negative direction. But in this question, they didn't specifically mention whether object P is moving to the left or moving to the right. Or object P might be even moving upwards or downwards. You don't know. Okay, so what can we do is we don't define positive as to the right. We don't define negative as to the left. We define a specific velocity, a specific direction of velocity to be the positive direction. So what I mean here is, if we take the direction of the initial velocity of P to be the positive direction, then now if the velocity is in the same direction as the initial velocity of P, then the component will be a positive component. But if the velocity of the object is in the opposite direction to the initial velocity of P, then this velocity here will be having a negative component. So we take a specific velocity, in this case the initial velocity of P, to define where do we set as the positive direction. So now if anything is in the same direction as the initial velocity of P, then it will be a positive direction. If anything is in opposite direction, the initial velocity of P, then it will be a negative direction velocity. Okay, so now we have defined the direction only we start to do our substitution. So for our substitution, we see that the initial X component of velocity for P is pointing in the same direction as UP because it is UP, so it's positive. Whereas for initial X component of velocity for Q is pointing in the opposite direction to UP, so it's negative. Okay, the component is negative because it's pointing in the opposite direction to UP. Next, you move on to the right hand side of the equation. You know that these two mass, you know the masses, but you know that the velocity here will be the same velocity. It's a common final velocity, so you can replace them with the same symbol and factorize out from the right hand side of the equation. Then now if you proceed, you see that Vx is 10 divided by 6, and you know that our x component of final velocity is 1.67 meter per second. Now see here, the x component of velocity here, it's a positive value. If you see it's a positive value, you know that it is in the positive direction. And if it's in the positive direction, that means it is in the same direction as the initial velocity of p. So now if you transform this component back into vector, component is value with negative or positive indicating the direction. Now you transform it to back vector, you have to write in terms of magnitude and direction. So if you write in terms of vector, you use a vector sign, you write the magnitude. Magnitude of a vector must be always positive, so you always put the positive answer for the magnitude. But for the direction, you define clearly, the direction will be in the same direction as UP. So after P and Q collide together, they will move in the same direction as the initial velocity of P. So if this diagram here is indeed the actual situation, then P and Q together move to the right. If P and Q flip position, then P and Q collide together, it will still follow the initial direction of P. So it depends on where we set P and Q is. And because it's arbitrary, right, we will just say, we know for sure that it will follow the initial direction of the object P. Okay, we cannot write left or right over here because they didn't define what is moving to the left, what is moving to the right. Okay, the purpose why I discuss this question over here is to make sure you understand the importance of the sign of the components. If the component is negative, it means it's in the opposite direction. If the component is positive, that means it's in the same direction as a certain thing that we define. Okay, so let's try to do another example for this. Let's say we change this 3 meter per second to 10 meter per second. Now we replace this with 10 meter per second. Now if you proceed to do the whole calculation, you still take UP as the positive direction. Then you change this to become negative 10. You change this to become negative 14. You change this to become negative 2.33. The answer that you obtain for the x component of final velocity will be negative 2.33. So what does the negative means over here? It means that it is in the negative direction. If it is in the negative direction, that means it is opposite the direction of UP. So when you write your final velocity will be 2.33 meter per second. Your magnitude should always be positive because this is a magnitude of a vector. Magnitude of a vector must always be positive. But for the direction, we write clearly that it is opposite the direction of UP. Because you find from the component that it's a negative, so negative direction is opposite the direction of UP. So magnitude, no sign, just keep it positive because it's a magnitude of vector. But the direction is state it clearly, it's same direction as UP or it's opposite the direction of UP. Okay, so that's how you do it in conservation of linear momentum. Now let's move on to a situation which involves the conservation of angular momentum. And we are going to solve this question now. So we have two disks that are rotating about the same axis. So this dotted gray line here represents the same axis. So the same axis that this A and this B are rotating. Okay, so this A has a moment of inertia of 3.4 kg meter square. So let me write it down. Moment of inertia is I. So moment of inertia of A is 3.4 kg meter square. And this over here, it's rotating with an angular velocity of positive 7.2 radian per second. Why is this question stating explicitly the positive sign? It's trying to tell you that this angular velocity it's in the positive direction. Okay, if we follow our usual sign convention, we usually say positive it's anti-clockwise. So if you follow that sign convention, then we know that this let's say this is this A, and this A here will be spinning anti-clockwise, so something like this. And angular velocity will be equals to 7.2 radian per second. Okay, you can put on the positive sign. Technically, if you put on a positive sign, then what you should write is you should write the component z over here. Technically, you should do that, but you can ignore the z because most of the book don't write the z. The z is just there to tell you that it's a component, it's not a magnitude. Okay, I'll write it the actual way of doing it, then I'll tell you that later you can just remove the z. Okay, just to tell you clearly this is a component. So because there's component, I'll include the sign to indicate the direction. If I remove the z, right, then technically this symbol here is the magnitude of angular velocity. If it's magnitude, right, then every magnitude should be positive. Then you cannot write in the negative sign anymore. Only by changing it to component, then only the plus and the minus represent the direction of the vector that is represented. Okay, so this B here is rotating with angular velocity of negative 9.8 radian per second. Negative means it is rotating in the negative direction. Negative direction, we know that it's clockwise. So when we label it over here, it will be something like this. So clockwise will be something like this if you view from above. Then this will be angular velocity of B, Z component. Z component means by if it's pointing upwards, then that is the positive Z direction. If it's pointing downwards, then it's a negative Z direction. We do our clockwise, anti-clockwise on the plane, right? So Z is pointing upwards, negative Z is pointing downwards. Okay, so this one will be negative 9.8 radian per second. Okay, now the two disks are then linked together without the aid of an external torque. So why do they say without the aid of external torque? Because if you remember, in conservation of linear momentum, you need to be an isolated system. So the sum of external force must be equal to 0. Only the linear momentum can be conserved, right? But for this case, since this is angular momentum, your sum of external torque must be equal to 0. Only your angular momentum can be conserved. So in this case, they say you don't have any external torque. Only your angular momentum will be conserved. But a lot of the time, we don't really write it so explicitly. But this is just to tell you the idea. Okay, so these two disks are then linked together, then so that they rotate as a single unit. Okay, so you do something to make these two disks click together. You can either combine them together, or you can use a rod to connect them, something like an axle to connect these two disks together. Whatever method, they didn't mention the method, you just combine them together so that they rotate as a single unit. So A and B will be rotating at the same angular velocity after they connect together. Okay, if you link together already, you have to rotate together. So the final angular velocity should be the same for A and B. Okay, so for this case over here, you can see that the final angular velocity is negative 2.4 radian per second. Okay, so probably I should write initial over here. I should write initial over here. Okay, then this one will be omega for A and B, omega Z final, and this will be negative 2.4 radian per second. Okay, so this is the rough idea of what is happening to the situation. Let's see what they asked for. Okay, so the axis of rotation for this unit is the same as that for the separate disk. Yes, that's what we do. Previously, it was on this axis of rotation. Now, after connecting together, you are still using this same axis of rotation. So it's the same for separate or combined. They share the same axis of rotation. Now, what is the angle? What is the moment of inertia of this B? So now they're asking for what is I subscript B. Okay, so to solve this question, again, we will use conservation of angular momentum. So the sum of the initial angular momentum in the Z component will be equal to the sum of the, technically, Z should be up there. A lot of the time, I'm not sure which one should be up, which one should be down. But I think this one should be Z component of angular momentum initial, Z component of, Z component of angular momentum final. So this is how you should start, because you know that the initial angular momentum and the final angular momentum will be conserved, so they should be the same. So you know that how many bodies are involved over here for this sum. You have body A and you have body B. So therefore you break it into Z component of angular momentum for object A. Now it's getting too many subscript already. Z component for A initial plus Z component of angular momentum for object B initial equals to Z component of angular momentum for A final plus Z component for object B final. Okay, then after that, you know that angular momentum is a product of the moment of inertia and the angular velocity. So now you can break it into moment of inertia for object A, angular velocity for object A, Z component of velocity. I'm a bit. Okay, I'll just do it the complicated way first, then I'll tell you what you can remove. The Z component of angular velocity for A. What am I doing? Okay, it will be A, Z initial, okay, plus IB, then omega, the angular velocity for object B, but the Z component only initial. Then IA, omega for object A, but Z component final, plus IB, omega for object B, the Z component final. Okay, now you can do your substitution. IA you know is 3.4. Omega you know is plus 7.2. IB you're not sure what's the value. The omega for object B initial is negative 9.8. So the negative is important. You have to include. Equals to IA and IB, they share the same common final angular velocity, right? So you can factorize out the omega Z final, then you can call it IA plus IB. Should have done this earlier, but never mind, let's continue. So this will be 3.4 times plus 7.2 plus IB negative 9.8. Your final common angular velocity is negative 2.4. That means these two disks, right, after they link together, right, it will rotate following the direction of the disk B over here. So it will rotate in the same direction as disk B. So after they link together, disk A will change the direction of rotation, whereas disk B will remain it's the same direction of rotation. Just that this whole thing here will slow down after they link together because the value gets smaller. But this one remains in the same direction. This one changed to the opposite direction of rotation. Okay, continue. IA you know is 3.4. What you do know is IB. Okay, if you look over here, this equation here, the only unknown left is IB. So you can key into your calculator, then you should be able to obtain the answer for moment of inertia for object B. And moment of inertia for object B should be 4.4 kg meter square. And this is how you obtain the moment of inertia for object B over here. Again, what we need to emphasize is we need to emphasize the direction. So for this calculation over here, we assume the positive direction to be the direction of rotation of this A. So if you are rotating opposite the direction of this A, like this B over here is rotating opposite the direction of this A, then you will get a negative component for angular velocity. So if you see here the answer for the angular velocity final here is negative. That means once they are linked together, these two disks are rotating opposite the direction of this A. You see negative, that means it's opposite the direction of angular velocity A. So it's rotating in the opposite direction to A just now. Okay, so what can I remove from this working over here? There's too many subscript, right? Well, in our syllabus, we don't really emphasize need to write the Z component. Okay, because in our syllabus, all the angular momentum is happening in the Z component. So sometimes because we have no X, no Y, only Z only, right? Sometimes you can just ignore the Z. Okay, so you can just ignore all the Z. You don't need to write all the Z here. So writing like this is also sufficient already. Okay, I'm just putting the z there to tell you that it's because that it's a z component, right? Only you can put in the positive and negative value. If without the z, right, technically this symbol here represents magnitude of angular velocity. So magnitude of angular velocity should always be positive. So technically you cannot substitute negative here. So what allows you to substitute negative is because there is a z down there to show that it's z component. But we are just too lazy to write the z component, so we just write it like this. Okay, so if you write it like this is also fine as well. Don't go purposely go write in the z. I'm just telling you that the z, there is a z there actually, allowing you to put in negative sign for your angular velocity. Okay, so that's how you solve a question for conservation of angular